Okay. So Angela it already started stream to YouTube, right?
Yes.
Okay, so let's start. So hello everyone, welcome to our 3D geometry and vision seminar talk. Today it's a great honor to have Professor Huang from Shenzhen University to share her recent works. Professor Huang's research interests cover computer graphics and visual computing, focus on geometry modeling, shape analysis, point optimization, scene understanding, and so on. Today she will share her recent works, and the talk title is Reconstructing Transparent Object. Okay, let's welcome.
Okay, thanks Jiyong for the nice introduction. So as announced, the problem I'll introduce today is about reconstructing complete 3D shapes of transparent objects with low refractive index. For example, if you can see the left side, it is the captured image of a real transparent object. And our reconstruction result is demonstrated in the middle, so which nicely recovers the object surface geometry. The left side is this reconstructed model rendered in a virtual environment, which correctly reproduces the light refraction properties. So the accuracy of the three-dimensional real-world objects or the phenomena is an important topic in the computer graphics as well as in computer vision. Most techniques that have been developed over the past 2 decades have focused on opaque objects with the assumption of that nearly lambation reflectance. So this property defines an ideal matte or diffusely reflecting surface. The apparent brightness of the lambation surface to an observer is the same regardless of the observer's angle of view. In other words, for the object exhibiting lambation reflectance, a surface point can be assumed to have the same color in the images taken from different viewpoints. Nonetheless, this is no longer true for the non-lambation surfaces. Large classes of the non-lambation surfaces phenomena pose huge difficulties for these traditional accuracy techniques, such as reflection and refraction. For example, both conventional laser scanners or the multi-view stereo-based methods would all fail on capturing this kind of like transparent objects. So why? I want to like give a more intuitive here. So the structural light is the process of the projecting a known pattern, like often grids or the horizontal bars on the screen, right? So the way that the pattern deforms when structuring surface allows the vision systems to calculate the depth and the surface information of the objects in the scene. A very interesting example, actually I show on the right, is proposed in this classic ICCV paper, 3D photograph on your desk in 1998. The authors call it weak structural lighting because of the simple and inexpensive setup. We have a desk lamp and a pencil and a checkerboard. So the cameras faces the object, which is illuminated by the desk lamp. The user moves a pencil in front of this lighting source, casting a moving shadow on the object. Then this 3D shape of this object is extracted from this spatial and camera location of the observed shadow. So this is kind of like how the structural light works. But here we show this is a projected structural light pattern and the corresponding 3D reconstruction for 3 types of surface: diffuse, that is lambation, a glassy, and specular. So as a surface for the 2 latter does not meet the lambation assumption, the projected pattern is hard to detect, and as this reconstruction results become worse from left to the right side. So if we use a structure-like scanner to scan a transparent object, like here, it is actually ATAC Space Spider, a very high-end scanner, still fail, cannot capture the meaningful shape geometry of this transparent mouse statue. Multiview stereo recovers 3D geometry from a collection of the images, as illustrated in the left side. I think all the people actually familiar with, but it's also based on the property of the lambation surfaces. State-of-the-art the MVS techniques can produce highly detailed reconstructions even from millions of the photographs. However, for a transparent object, the lambation reflectance assumption breaks. MVS cannot properly handle this light transport phenomena anymore, so fails, as you can see in the right video. So speaking about this related work, previously, a stream of the works focused on the reconstruction of the inhomogeneous instances, like the flames, gas flow, fluids, clouds, and so on. Differently, what we consider, at least for today, is all about solid, transparent objects. Then for this challenge, transparent objects, there exists some like intrinsic approaches for the reconstruction. The most direct method is to pen and scan. Actually, we also use this to create our ground truths. Others consider to immerse this target object into the liquids. Then it is possible to infer the geometry using the laws of the physics. But an obvious drawback would be the immersion itself, because it is not suitable for objects with delicate geometry details and also probably can destroy these objects. In comparison, our method is designed as a non-intrusive method. Then, inspired by the law of the refraction, people started to investigate the relation between the geometry and the refraction properties, like marrying the light ray paths traversing through the objects and then requiring the surface by optimization. But due to the high optimization complexity and the heavy computation, a full successful 3D reconstruction was hard to be achieved. Under the hot wave of the machine learning techniques, quite a few researchers deal with transparent objects by the deep neural networks. Like Ni et al. From University of the California, San Diego, use these neural networks to predict surface normal and reconstruct the point cloud of the transparent objects. Actually, I'll give more comparison later. So their experiments show successful recovery of the 3D geometry for the complex transparent shapes using as few as like 5 to 12 lateral images, which is quite amazing. But also due to the input and this data-driven nature, their results are usually over-smooth with relatively large reconstruction errors. So recently, differentiable rendering is an emerging tool enabling the inverse analysis of the images. To name a few, like Ni et al. Introduces a general purpose differentiable ray tracer in 2018. Nimo David et al. Proposed this actually wonderful tool in 2019, which could be applied in the computational acoustic design. More specifically, DR can be used to determine the shape and the material of an object from one or multiple input images. For example, say here, rendering a scene using a realistic light transport simulation can be interpreted as evaluating a function here, fx, whose input x encodes the shape and the material of the objects. Owing to the complexity of the function f, an inverse function to retrieve some parameter from this existing image y is usually not available. So differentiable renderers pursue such an inverse by differentiating f and casting the inversion into a gradient-based minimization process. So this existing DR methods can be classified into 3 categories based on their geometric representation: point-based, voxel-based, and mesh-based. Voxel-based DR is mostly used when considering volumetric scattering, such as smoke, cloud, the music in homogeneous instances. The mesh-based DR is by far the most popular, I would say, especially when it comes to the most of the complex physical effects. The transparent objects also belong to such category. So we have explored both point-based and mesh-based optimization framework for our transparent objects reconstruction. So we published 2 papers about this topic. One is in SIGGRAPH 2018, another is in the most recent SIGGRAPH Asia 2020. So in the first work, we presented the first non-intrusive method to reconstruct the full shape of a transparent object. We optimize a few pieces of the point cloud and merge pool. Okay, so I think I just introduced a bit of like a background of this transparent objects and both the, I think that both the structure and the MVS technique will fail on the capturing transparent objects. And I also introduced a bit about the related work from the intrusive, the techniques, MVS techniques, and the differential rendering. So after that, then now I'll start to introduce our approaches. So we published 2 papers about this topic. One is in the SIGGRAPH 2008, and another is in the most recent SIGGRAPH Asia 2020. So in the first work, we presented the first non-intrusive method to reconstruct the full shape of a transparent object. We optimize a few pieces of the point clouds and merge them together with the point cloud consolidation techniques. So this is our first attempt. So surely there is a large room to improve. This year, we made some visible progress. Instead of fusing the point cloud, we directly optimize a surface mesh. Better results are obtained with a much simpler capturing system indeed, and a more concise the reconstruction pipeline. So let me start with some simple physics related to transparent objects first. So when an ray travels from a medium with refractive like index R1 into one with a refractive index R2, the part of the light is transmitted, right? And it bends. So Snell's laws tell us this equation. So it can be used in the ray tracing to compute the angle of the refraction, and is also the core of the rendering of the transparent objects. It describes the relationship between the surface normal and the direction of the refraction. So if we know this ray pixel correspondence, we might use it to determine the depth of the intersection point and the surface normal. However, this is an underdetermined problem, even in the case of the single refraction. Consider that a ray travels in another medium and ends at this point. I write here the Q in the second medium. So the multiple combination, if you can see from this right, the illustration, this multiple combination of the surface, the depth normal can all satisfy the Snell's law. So the surfaces of this different depth value, like the O1, O2, or O3, all corresponds to the different normal vector Ny, N2, N3. This all meets this refraction relation. So we call this depth normal ambiguity exists. So how to eliminate? We show the two simple schemes. One is to using the two reference points, like by observing the two different reference points in the direction of the outgoing ray, such as the Q1 and Q2, the exit ray direction Q1, Q2 is determined, right? So then we can compute this separation of the intersection point and the normal vector. Did I lose my collection? Hello?
No. Yeah, I can hear you.
Oh, okay, because I cannot move my screen. Okay, so sorry. So another is using two camera views. That is, we use two cameras, P1 and P2, to observe the same like hypothesis point O on the surface, and find the reference points Q1 and Q2 in the direction of this outgoing light, respectively, and calculate two normal vectors Ny and N2 that satisfy the law of the refraction. Since the norm of the vectors at the same point on the surface should be consistent, so it can then be restored. So an immediate question is how to capture this refraction data? I'll start by introducing this environment mapping. We know that mapping is a process of considering with this extracting from an image a scalar for foreground opposite the map, right? So environment mapping is an extension of the mapping that also captures how a transparent foreground object distorts its background, so it may be comparated over a new one. If we assume that each pixel on the foreground image is only related to a pixel on the background, we can think of the environment mapping as a ray pixel correspondence. The ray starts from the camera viewpoint, ends at a pixel on the background, marked as the red arrow here and the red square. So this pioneer work of the Juncker itself in 1999 extracts this environment mapping from a series of the projected horizontal and vertical strip patterns. After obtaining this ray pixel correspondence, we rotate this background monitor and capture the data once again. Then we can collect this Q1 and Q2. This ray pixel correspondence is converted to the ray correspondence, which means that the very first ray that enters the transparent object and the last ray that exits this object, marked as the red zone here. This is actually proposed by Chen et al. In CVPR 2016. So on the other hand, we can also rotate this transparent object itself to capture multi-value data. As I just mentioned, these two reference points and the multi-value data are important to eliminate this depth normal ambiguity. So based on all this knowledge, we build up our own automatic capturing setup. By positioning these transparent objects, if you can see on this Turner table, this object will be rotated and observed in different view angle with respect to the camera. Then this monitor will simultaneously display these gray code patterns, working like this. Then after capturing, we can reprocess this captured data and compute this ray correspondence and the silhouette of the objects of the different view angle. Actually, I will show more later. So suppose now we have already captured this ray correspondence by a camera. which means that the relation between the very first ray that enters the object and the last ray that accesses the object's market, as is red zone in this figure. Then by this backtracing of a ray, we could find these two intersection points with this pre-assumed like objects. I denoted here as P1 and P2. So if there only exists a strong assumption, like two refractions, after collecting these 2 points, it will generate a complete light ray path. This is very important, so I'm kind of like repeating here. So by computing this surface normal and the Snell's law at each intersection point, we could then formulate an optimization that constrains this consistency between them. After optimization, this is the intersection point will be updated to satisfy this law of refraction more closely. By the way, because of this limited view angle of the camera, this recovered point cloud will only like cover a part of the object. Like here, it's a front and back region in this example. So in order to reconstruct a full shape of objects, a straightforward method would be to capture ray correspondence from different values, then use optimization I mentioned just now to generate the point cloud. So we have actually tried directly merge all these pieces together and do the reconstruction. But as you can see, the result is misaligned and very noisy. So here comes our idea. We start and the initial model, and then it will be optimized gradually to achieve a satisfactory results after several iterations with the necessary geometry details recovered. Compared with the ground truth as visualized with this color map at bottom, the average distance from the reconstructed models to the ground truth decreases effectively as expected. So therefore, this is the final result looks pleasing. In particular, I'll go into detail now. We start the optimization from an initial model generated from the shape from silhouette. Then we apply the normal consistency mentioned before to obtain the optimized point cloud at the beginning. Then we have proposed 2 novel like a point cloud consolidation method to refine these points, followed by the Poisson reconstruction to reconstruct a 3D mesh. Like after several iterations, the whole algorithm will output the final reconstruction result. So next, I'll elaborate these 2 consolidation techniques. That's kind of like the technical meat here. So the first one is a surface projection. As illustrated just now, the directly merged point cloud is very noisy and misaligned as shown here. A straightforward like idea would be, okay, we first do the denoising. What I use here is the WLOB, a robust denoising algorithm actually proposed by myself, my first computer graphics work in 2009. So with this, only one parameter needs to be tuned, the radius of the local neighborhood property. So it turns out neither a small radius or like if I say neither a small radius or the large radius are suitable, because the result is either noise or otherwise over smooth. On the other hand, we observe that since we have an initial model, right? So the samples on this initial model are indeed complete, although inaccurate. We also have optimized point clouds that satisfy the law of the refraction, as it is relatively accurate, but incomplete. So does this exist a method that could combine these 2 in order to generate a complete and accurate point cloud? We propose an adaptive radius based on the surface projection algorithm to achieve this. As you can see, after optimization of the previous step, the concave region on the surface is better captured by the optimized point cloud as marked green here. and compared with the sample marked as gray points. So instead, this convex region could be well estimated by both points. So we consider to use an adaptive radius to project these samples on the initial normal A to optimize the point cloud B. So as shown, a large radius should be used when the sample is far away from the optimized point cloud, while a small radius is preferred when they are close. So after projection, this reconstruction is much better than before with more details recovered. Here is the math behind it. So we tried to minimize the distance between A and B with this controlled radius, which is enabled by this descent the function. So the effect of this function is determined by this adaptive radius. And for more detail how to compute it, it's better to read our paper. Okay, so in order to have a more intuitive understanding about this, let me show this. The projecting these sample points using this adaptive radius results in a consolidated point cloud in red that obviously better captures the shape of the kitty around its ear and the back, right? So well maintained to be smooth. So please see this cross-section curves as shown here. Okay, so let's check this pipeline again. Since we now can output a complete and smooth point cloud, so think that if we remove this second part from algorithm, so what will happen? So after 25 iterations, we plot this average distance of these reconstructed models and its ground truth. We can see the improvement is not very obvious. Here is an example of the result from the 20th iteration. It's rendered as a transparent blue compared with the ground truth. The ear and the tail region is far from satisfactory. So the reason is there may exist multiple possible surface that could satisfy given this rigid correspondence, like the surface 1 and the surface 2 marked here. So actually, if this initialization of each step of the optimization is not very good, oh, I go fast, yeah, this result could be stuck in this local minimum and get worse. So based on this observation, we propose the silhouette consistency. In order to extract the boundary, we first project this point cloud onto the image plane of each camera. So the area covered by the points is determined by the KNN graph. Then we extract the boundary of this area. So since we have already obtained the silhouette of its objecting a different angle, so during this pre-processing stage, we can constrain this consistency and between this extracted boundary and the silhouette under each camera view. So this is how we make it. The QJ is a projection of each 3D point, and this is the orgama is the silhouette. Then if this projected 2D points is on the boundary, we'll try to minimize the difference between the boundary and the silhouette. So this is the detailed equation. So then let's see the results while considering this silhouette consistency constraint. So after the same number of the iteration, this reconstruction result marked as a transparent orange here is obviously improved. So after 2 phases of the consolidation use different constraints. So a real 3D surface is generated from the resulting point cloud using Poisson screened surface reconstruction. And this real model can be served as a rough shape for the next round of sampling, normal consistency, consolidation, and reconstruction. So this is another synthetic bunny model to show this progressive process. After several iterations, the distance from the reconstructed model to the ground truth surface are visualized as area maps at the bottom, which demonstrates the effective of this whole pipeline. And this results visually compares the rendering results of this the ground truth model and our reconstruction in the same environment, under the same view. So can you tell which is ground truth? Okay, so this suggests that our approach can nicely reproduce the appearances of the transparent objects. We also test our algorithm on several real transparent objects. The combination of these complex object shapes and cluttered environment leads to these high frequency signals in these captured images. This one shows this image captured for the one is hand study. Our algorithm starts from a rough model obtained using space carving and progressively enrich it as shown here. So the final converged model is smooth and nicely captures the surface details in the concave area. To conduct the quantitative evaluation, we actually paint this transparent object and carefully use this high-end scanner, scan it as a ground truth. Then the average reconstruction error curve shows that our approach can in fact reduce this reconstruction error and converge after only 20 iterations. So here are the reconstruction results for the monkey and the dog, all the real objects. So for each object, this reconstruction, the red column, and successfully capture this feature with the concave parts, right? Highlighted in this green box. Nonetheless, we can still observe the area a lot well reconstructed, highlighted here in red, due to the violation of the two fraction assumption. Since these reconstruction artifacts only show up in the area involving multiple refractions, they are hardly noticeable when comparing this rendering of our reconstruction model. If you see this middle column with the real object and the photo and the left column. So this is another reconstruction of this real transparent mouse. So while the shape of the object is well recovered, the results tend to smooth out some geometric details. When we can reconstruct a full shape, we are getting pity. Now we can care about this fine geometry detail. So compared with this new method we proposed this year, you can clearly see that the details of the eyes and the tummy are better recovered. Okay, so how did we improve? Firstly, we actually skipped this point cloud, the fusion step I just introduced, by using differentiable tracing of the refractive passes to directly optimize a 3D surface mesh approximation of the object. So directly using this triangle mesh representation, we successfully merged these multiple constituents I just introduced into a single objective function, which resulted in a more concise framework, and we can use the DR technique as an optimizer. And in order to accelerate optimization convergence and better avoid the local minima, so we also propose to optimize this mesh in a cost-to-fun fashion. So now I'll introduce them in more detail. Again, starting from an initial mesh, here in the mesh, we gradually remesh and deform it to recover more and more detail. The cost stage of the optimization introduces a large deformation of the optimized 3D mesh, while the fun stages recapture and recover delicate geometric surface details. So along with our exploration, we also found out that this correspondence is somewhat redundant. We somehow do not really need a rotation background monitor to capture this real correspondence. Why? Because the environment mapping tells us how a transparent foreground object distorts like its background, right? Actually, I just showed the GIF. So this extension from the mapping to reconstruction, this ray-pixel correspondence is actually enough in the sense that we can directly optimize the reconstructed shape of the object to better match a collection of the environment matters captured from the multi-view. So we successfully simplified our capturing system this year. So with just a static monitor and a code pattern, we establish a mapping between the camera view rays and the location on the background. Specifically, doing this accuracy, this turntable of the object is rotated to provide multiple view of the data. At each angle, these gray coded background patterns are displayed on the monitor. So this is this is the captured images shown on the right. You can see this object distorts its background due to this reflection, right? Okay, so now our goal is to reconstruct a virtual 3D model which can reflect this background in a manner consistent with this captured data, captured image. So for each view, the captured image are used for extracting the objects, the silhouettes, and estimating this environmental mapping. From this collection of the multi-view silhouettes, using this space carving, we reconstructed this convex hull as our initial mesh. Now we have this initial model, which is then remeshed and deformed intuitively. So now let's figure out how we optimize this surface, optimize all we say the mesh deformation in detail. This mesh deformation is guided by a single object function, making use of a differentiable refraction tracing, which consists of the three losses: refraction, silhouette, and smoothness, with all differentiable operation. So this refraction loss plays the similar role of the previous norm consistency I just introduced. It constrains that this is the reconstruction mesh reflects the background in a manner consistent with this environment mapping. But this time, let me show again. Oh, somehow started. Okay, but this time we do not need this ray correspondence. We trace a ray in the simulated environment with our reconstruction mesh. The simulated ray path is shown like in orange here, and it would reach another point on the monitor. Let's call it Q prime. As before, we only make use of this ray path that reflect directly twice before reaching the background. So point is Q and Q prime are generally at different position because of the difference between the constructing the mesh and the real object, right? So this refraction loss is defined as to minimize the distance between this Q and Q prime. Very intuitive. Then we can see as this refraction loss decreases during the optimization, this mesh better matches the environmental matrix and reproduce more accurate light transport. Okay, so then the silhouette of object is somehow similar as before, but it offers an important constraint for the boundary of the reconstructed mesh. So it's inspired by the related work in the SIGGRAPH Asia 2018, which actually deals with the discontinuities by the edge sampling. We introduce our this differentiable silhouette loss here. We use this gray pixel of the image represent this captured boundary, and this yellow polygon to represent the boundary of the reconstruction mesh. The projection of this yellow polygon would match this gray pixels. Let me use like a simple sketch to better illustrate the computation of this loss. We need to constrain this yellow boundary to match the gray pixel, right? So for simplicity, this midpoint of every edge serves as a representative to determine whether the edge is in the green pixel or not. And the shape of the reconstructed mesh is used to determine the direction of its gradient descent. So case 1, if this point is inside the mask, located in this red pixel, the edge would move along the edge normal, which points to the outside of the reconstructed mesh. Conversely, if this point is outside the mask, located in this black pixel, it would move to the inside of the mesh. Also, if the point is on the mask boundary, its gradient is set to 0. So the English study shows that the necessity of this silhouette constraint. Without it, we cannot maintain the correct boundary. And our final loss is the smoothness. This term ensures the smoothness of this virtual model. It measures the difference between the normal vector of the neighboring triangles. Okay, so with these 3 losses in one objective function, here are some like synthetic results. The bottom row visualizes the per vortex reconstruction error. Obviously, these errors are significantly reduced like as this optimization progresses. The average error also decreases roughly to the 50%. Comparing with our previous method and the ground truth, clearly this new results captures much more finite details. We have also enriched our real object collection. Like we have both the horse, the pig, and the tiger shown here. So our reconstruction model succeed in capturing some delicate like skin folds and the wrinkles on the bodies of the tiger, as well as the whiskers and the eyes of this rabbit. The reconstructed hand model is showing on the left, comparing with the ground truth we built by the pin and scan. Both in this rendering and the pure geometric models, we can clearly tell how accurate the reconstruction model is. Let's zoom out the fingers to look more closely. It is still difficult to tell, right? The difference between our latest results and the ground truth. We have achieved like a significant improvement in reconstruction accuracy by utilizing this differentiable refraction tracing. There are 3 more models, all are like our reconstructed results. Like a more comparison with the previous results I show here. If zoomed in, our latest results preserves more visually meaningful and pleasing geometry details. Note that the arm of this monkey in the reconstructed of this CVPR order work is faithfully collected with the body due to the lack of this silhouette constraint. So ours is correctly reconstructed. We successfully recovered the detail of the eyes and tummies of the mouse. Note that only the tail of our latest reconstructed mouse maintains the correct topology. The doll statue also presents similar comparison results. Okay, so if you follow me closely until now, you might like to raise a question like on the main assumption. That is, all ray paths that we captured and compute will lead to like exactly 2 refractions. This sounds quite limited, but indeed is actually much less restrictive than it seems. Note that in our system, each object is captured from multiple view directions. We measure this is the percentage of the mesh triangle that are pierced by at least 1, like 2 refraction ray paths. It shows that most mesh triangles actually ends up having two refractions ray paths passing through it. We also visualize the number of the two refraction paths by person each triangle under the 17 tube we use. So the reconstruction error is shown here. Clearly, in general, the number of these two refraction passes tends to be smaller for those triangles parallel to the camera VU rays. So it demonstrates that this two refraction assumption is indeed, actually, I think is a very smart computational design rather than an implementation for such actually most general shapes. But still, when it might fail. So here is a failure case. This is a shell model, has this shallow part near the opening. From all of this VU, it requires like more than two refractions for rays to pass through this big concavity part. It does not satisfy our two refraction assumption. So that is to say our approach fails to reconstruct this object with such big concavity. Okay, so it's time to conclude. So today I don't know if I show here some wrong. This slides, okay, let's ignore it. So today I elaborate how to fully and automatically reconstruct this transparent object. So there are some like insights and the message to take home. This environmental matching is actually not limited to one-to-one correspondence, actually. We can locate like multiple contributing sources from the surrounding environments, especially for the diffuse transparent objects. And what's more, this reflection is probably an important contributing source at this glazing angle. Besides, it's might possible to estimate this refractive index based on this environmental matters, which would largely extend this is a potential application of the transparent object reconstruction. In our framework, the topology of this mesh does not change, like the topology does not change during the optimization. So it is important to obtain like a good initial mesh. Can we relax this requirements? That's interesting to explore. Further work would also attempt to alleviate these two refraction restrictions, especially for the objects with these big cavities, like this shell model I just showed. Okay, so big acknowledgement to my dear PhD student Bojian Wu and my master student Jiahui Liu, and also to my close collaborators Yang Zhou, Minun Gong, Danny Winshinsky, and Daniel Huang. Without them, I certainly cannot go this far on this research topic. So we have shared our source codes and all captured data at our VCC official web. Welcome to try. Thanks for the listening. Now I'll take questions.
Okay, thanks to Professor Huang. What we'll do next is a Q&A session. We already have some questions from YouTube. So there are also some open questions to the panel. So Angela Yao from NUS and Wei Shi from Zhejiang University will join us together. Okay, so the first question from YouTube is that, is it possible to handle the case that some parts of the object are transparent and the remaining parts are not transparent? So it's like a mixed, so some part is transparent and some are not.
Okay, so this is actually an interesting question. So actually we haven't tried, but I think it's quite possible because of when we capture, if we have this partial part as transparent, we can still capture this ray pixel correspondence, and we can still like capture this differentiable ray tracing. So we can still like reconstruct the part of this transparent this transparent, I think, the area. And for other diffuse model, we can directly just by this the diffuse capturing, right? So I think maybe there are some like a fine detailed registration between boundary properly. But I would think if we set up this accuracy and computation correctly, I think this like just the simple SAP would do the job. So I think this is quite possible. Just need some, I think need some engineering work to get it to work.
Okay, yeah. So the second question is that I wanted to know whether transparent object reconstruction has any relation to CD search.
CD?
I think it's like a CT image. Yeah, I guess. So
okay.
Yeah.
This is actually somehow is like what we make is the medical image, right?
Yeah.
This but I think it's a CT image. If for me, like actually, I don't know much about it. But for the CT image, for me, it's more like the slicing, like an image on like the volume, right? So this is kind of like I cannot so far I cannot collect this too, but I would think some like there is a voxel-based DR. Actually, I know it have been like applied to use this kind of like a CT image-based 3D reconstruction. I think this I would say this probably has need to have the different consideration by my knowledge on these CT images.
Okay, so our other question is that can this algorithm handle multiple disconnected objects at once?
Multiple disconnected.
Yeah.
So this actually is an interesting, I think it's a very good question. So because if I okay, let me show here. So say the first message. So because actually I would say currently our accuracy system is also a very controlled the lab environment. So it's actually like the single objects and actually in the dark room and then in the with the display and the camera. So that we can actually more accurately capture this pixel to ray correspondence. But if you have multiple objects, and actually I think this light transport, this refraction, and also the reflection would be much more complicated. So I think this would be the very special, if not possible, but it would be very like a special design for the capturing. If we can like a capturing and this properly, and also we can somehow model this kind of like this light transport. Basically, that means I indicated here is a multiple contributing light resources causes refraction and reflection. I think the same algorithm part can do the job. But the most difficult part is to establish this correspondence. So this is actually interesting. Actually, this is what we are considering carefully. So this is so far I can say is this.
Okay. Yeah. Okay. Two more questions. So the first one is that except the silhouette loss with the differentiable rendering loss. So from the slides we can see that the silhouette loss contribute a lot to the reconstruction accuracy. So the question is that is it possible to extend it to the inside of the object? So basically, the current method only applies the differential rendering loss on the silhouette, so not on the inside of the object. Right?
So I think it's if this like express the move, I think that here we also apply this actually we apply this differential rendering the technique actually in this single like objective function. So this actually considers 3 losses. So actually, I think I would say here the most important part is a refraction loss. So actually, basically, if you can also say here, this is a refraction loss to minimize this the distance between this q and q prime. That plays a key role here, and this is also differentiable. So basically, this actually so it's not just only the silhouette the losses, but the silhouette losses indeed and this very good. I think is a very good the geometry constraint to this geometry and also eliminate some of the ambiguity. So this is what I together. So I didn't really get the point of that question, but I would say by our application study and by our design, this is 3 losses together with this single object function is very like coherent and important. It's not just the silhouettes. Yeah.
Okay. So the last question from the YouTube is that is it possible to extend this method to handle some real-time rendering of a liquid?
Right. This is also so actually we are thinking about it. Actually for the liquid, especially like for the water, for this water surface, we somehow think is actually the simpler because it's one surface. It's actually only can like just do the one refraction, and but for this rendering is like insight is like how to like communicate like this capture is dynamic this light transport or some that I think is interesting. But because here by this I would say our problem is very specific for this solid transparent object with this 2 refraction like the substitute, which means you enter in and you out. So this setting is not suitable for that. But this refractive loss and this kind of like some insight by we use this DR, I think could be inspiring. So actually, this is also somehow we are kind of like looking for and trying to extend. So yeah, this is my coins.
Okay, thanks. So next, maybe we can go to the panel discussion stage. So
so I'll stop sharing the screen.
Yes, I mean, yeah, right. Maybe we can turn the camera.
Yeah.
Okay, so in the panel discussion stage, maybe Vivi and Angela can raise some questions, and then we can discuss. So maybe Vivi, can you start first?
Okay, thanks. Okay, so very good job. So congratulations to Professor Huang's great work. So I think it's very important to break the numerical surface limitation in the future 3D reconstructions, so in real life. So when we are trying to capture objects, there are reflections or some shadows, transparencies. So there are many problems in 3D reconstruction actually, because I'm involved in some development of 3D scanner or something like that. So I think there are many limitations. So so a question is, do you think differential rendering is beneficial to the reconstruction of objects with highly reflective surface?
So yeah, I actually so far actually we use this DR more like as like the like an optimization tool, I would say. It's like okay. because if you think about like our previous work, actually by that time we're also thinking about like how to like optimize this whole, like, because before we actually do like the several steps. We actually also tried to how to fuse this with, like into one single optimization, but we actually were failed to nicely to solve that optimization function. Yeah. So I think in this the latest work, we don't like change or like improve like this differential rendering like to. Actually, we I think we nicely use it to as like optimization to solve our objective function. So make this all our like all like differentiable and get the more accurate like the results. So I think this is kind of like how to say a smart design, and in this type we only consider the differentiable refraction tracing. And I think if we consider for this highly like spectral objects, like with this reflectance, I think it's like we can consider it for this the glassy, for this the metal. Also, it could be this is a differential rendering tool can be applied, and I think it's even more suitable for that kind of setting. So that is also kind of we are considering. So speaking about this different rendering technique itself, actually we didn't. I think we just use it. We didn't improve it.
Okay.
Yeah, so maybe Angela can also comment on this question or ask some questions to Professor Huang. Yeah.
Yes, so I was actually wondering how, because as far as I understood at the moment, you're assuming that the objects that you're working with are completely transparent as you're showing here, right?
Yes.
But how common is this for real objects? Like it has to be this, completely clear glass like you're showing in your examples, or do we have other types of objects which are maybe don't have the same level of transparency? Like, do we have to make strong assumptions on the refractive index now and so on?
Yeah, this is the good question. So actually we tested, it's maybe not, so also is a question about like, this is like a fully clear transparent objects. And probably if you use like, and actually we assume is a fixed refractive index. So which means like it's kind of like the homogeneous material. Yeah. And if you have like the mixed, and if maybe you have a color, and if you have kind of like a different, that would be all change. So I would say this is our first step towards. So we first like get this the full reconstruction, because this is for the reconstruction is really challenging. You very hard to capture data to compute, but it's also, I would say, the currently still at the beginning. You just scratch the surface. It's limited. It's although we can like, I think this is the if it's a fully clear transparent object, this accuracy can reach to like the millimeter, but if this is like a break our assumption, like the multiple material, and this means like, but multiple material actually is okay. If like is because we only measure is in and out. But if we have like a kind of like, if with different, this reflection is also big. And also is like some color, like influence kind of capture, all these index, this refractive index is maybe changing. That would, I think, would destroy this kind of like currently the accuracy we achieve. So yeah, this is a long way to go.
Following up on that, then, if you're working with a like semi-transparent object, would you still follow the same sort of approach and just adjust the design modeling, or would you actually start from a different type of approach then?
Actually, we tried some. Actually, I don't know how to speak English, but this kind of so that is kind of like the semi-transparent. But if it's like with a single material, and if all we can capture, actually we tried this we can achieve the quality results.
Okay.
The object is like the ring, it has a very simple kind of shape. So and otherwise it's too expensive to buy. So yeah. So, but I think for that is we actually tried out some simple we can do. That is okay. Yeah, I think the more challenging is like if they have like a break this kind of like a reparse. Break our like make assumption on this the correspondence, this mapping. This kind of like basically we cannot use the same object function to optimize it. That would so yeah. That actually I think it depends on the objects.
I see. I have one last question actually as follow-up is because I was looking at your setup with where you place the screen behind your object. Yeah. And I was wondering if you actually, are there no interferences from reflections from the screen itself or from the light source of the screen itself as well?
No, currently, actually in real it is, but in our computation, actually we assume is all the lighting is just from screen. Yeah, so this is, I think this is also like, so that's why it's needed to be captured in a dark room to somehow to issue this, but yeah.
Okay. Oh, it's good. I don't know if Weiwei or Juyong also have additional questions.
So I have another question. So, so besides except the silhouette loss or rendering loss, so for other rendering differential rendering loss, you need to know the properties, optical properties of your object, so you can do the retracing or path tracing correctly, right?
Yeah.
So how do you know the optical properties of the target object?
It's a property where it's basically it's a refractive index, because this refractive index actually determines the angle of the refraction. Yeah. So we assume.
So yeah. So if we want to generalize a method to others, something the object you just mentioned, like jade, something like that, it's very complicated object, right? So they have very complicated properties. We call it in graphics, we call it heterogeneous material inside. So I think it's also it is still very difficult.
Yeah, so that is like actually we were thinking about like if we have like an outloop optimization, somehow it's like it's more.
Yeah, you need to solve the shape and the optical properties at the same time. Yeah.
Yeah, it is.
Okay, so I have one question for the three experts. So it's a very general question, maybe not related to this talk. So recently with the popularization of a deep learning based method, implemented function based representation like SGF are commonly used to represent the surface. Meanwhile, it's like a differentiable rendering is also widely used. Such that the image and the video can be used to guide the 3D reconstruction process. So my question is that how these technologies will influence the geometry processing community. For example, in the past 10 or 20 years, we mainly works on like a triangle mesh or polygon mesh, but right now do we really need a triangle mesh? So maybe we can directly work on the SDF function represented surface. And another question is that based on this new technology, what new opportunities where we have? So
yeah.
to make, yeah, okay.
This is actually the general question. Will you have a comment?
Okay. So I think you first, Nettie first. So
okay,
follow you.
So I think this is quite general. So basically based on this kind of, I think now we have this is the very like popular get this the deep SDF, meta SDF. This all kind of like the implicit representation. And also this, like the latest is I think this the lips, the works is like especially like the how to like do this mesh representation from this implicit fields.
Yes.
So this is actually also what not on this topic, but it's on our like this urban reconstruction. We also I think considering the same problem. Because like if you capture the image, like multiple image with John, right? So then use the MVS, you can compute this like the point clouds. Then but somehow you generate this kind of like you have this the implicit field representation by the SDF but like when you do like use this deep learning work too, it's like if you only consider like inside, outside the kind of like binary, is actually like often cause like I think corruption, right? So, but if you consider this like this continuous distance with a less theoretical property, but this is computation is very high, and so actually I think we are also kind of have the same problem and trying to solve is like, okay, how to like this is the kind of like how to find some like representation between this the binary and the detailed distance to somehow to generate this the mesh back mesh representation from this implicit, and you also use this kind of learning approach. This is under consideration, and I think if you read this the latest like CVPR work like BSP9 and also is the convex net, it has two actually I think the constructed example, one binary, one distance, and both has. So we are kind of like now considering something like the middle level thing. That's what I can say.
Okay, very good. Also, yeah, I learned a lot. So, can you
conclude?
Comment on this question.
I just follow Huang's comment. So, yeah, so deep SDF or it's a very interesting representation, right? You input a point 3D position, then you get a side distance value. So I think the main purpose for this representation is to break the resolution limitation. So originally, if you use the volumetric representation, you need to have a resolution, right? So you cannot use too large resolution like 1000 by 1000 by 1000. It's very consuming. So they developed this kind of representation to handle such kind of issues. So I think that's the main point I can see from this approach. So, but from another perspective, I think it's quite time-consuming to construct such kind of representation. So that's the main problem. It's also another issue with this representation. So both it has strengths and weakness. I think it depends on applications. It depends what you want to do. I think recently, so if they use deep SDF to, I think they use the deep SDF to reconstruct light field, to record light field. If you take multi-view images, you can use this representation to reconstruct light field. I think it's quite impressive, right? They achieve very good free viewpoint rendering result, very high quality, very high resolution. I think it's quite impressive. But on the other hand, they need to train need to optimize such kind of representation by optimizing for a long period of time for a thing. So, so I still think it depends on what you want to do in the application. If you just want to do a free viewpoint rendering, so you need a geometry representation as a base, so you can use layered mesh representation or something like that. It's maybe lightweight and more, how to say, more easier to construct, right? So if you want to, if you want to get very compact representation for use in the future. If you just want to record it, I think you can use DPSDF. So if you want high resolution, you can use DPSDF. So that's my basic understanding, but yeah.
Okay, thanks. So Angela, can you comment on this question?
Sorry, so I'm not too well versed in these methods. I was going to follow up with some general comment actually about because we're working with differentiable renderers, because one of the common problems that we face, at least within Vision, is having access to enough data. But once we start working with differentiable renderers, you can also generate a lot of your own data, whether this actually changes the problem for you. And you can also apply this in doing self-supervision and so on to help improve the accuracies.
Okay, so yeah, it's also a very good point. So you can use such kind of representation to generate new data. So yeah. we are considering the render implications or reconstruction implications, but we can also consider self-supervised training, something like that.
Yeah, but rendering is actually the very purpose is to generate, right?
Yeah.
Okay, so any more questions from Wei and Angela?
No, I think it's pretty good. I mean, I think what would be nice actually to comment on, to conclude the session, maybe from Professor Huang and also Wei and also maybe Jion, is what you guys think the role of deep learning has in graphics, because I think it's slowly also permeating the entire field as well, and whether you think that this is a trend that will continue and how this plays with respect to this. I mean, because one of the key issues in deep learning is also having access to good data, right? So this is what I was leading into before. If you guys have any comments or thoughts on this.
Okay.
I just briefly say, so yeah, indeed, actually, now we also call our computer graphics like intelligent graphics, right? So
yeah.
So I think this is like I think this kind of like merging, the combination is kind of unavoidable, and I think it's actually good for our like field to be, because I think take the topic today as an example, like always this DR techniques, actually we can better solve this optimization, so we get this much good like results. So I think this is a good example to say actually now we have a much stronger tool, but with this tool, it's like I think also like a computer graphics researcher, I would think it's like how we like better use this more like this geometry understanding, this geometry constraint, and like better use this kind of like learning techniques to together to do more, I would say the good graphics research to solve like a problem before we cannot solve. Yeah, I would think this, and also you can see like especially on 3D. The 3D data set is still, I think, comparing with the images or videos, is still, I think, the weak part. So that is what like is also a kind of like a promote encourage us to how to like to generate more 3D parts, and not just geometry, but with this all like rich like the semantic information, iris annotation to somehow stimulate this the learning part back on the graphics. I think it's kind of like the iteration, the loop. So yeah, that's, I think this is the clearly a big trend. I'm kind of just repeating.
Wei, do you have anything to add to this?
Oh, this is a very fundamental question, I think. So yeah. So I think DI is a tool to connect the visual result and your input. So I think if we have good DI tools, you can directly optimize your input according to your output. So I think it's a kind of things to connect. So if we have a lot of data, we can learn. We can let the network to learn directly influence how your to directly influence the input. I think maybe it's a chance to boost the performance of graphics. So in graphics, a difficult problem is how to create high quality content to render very high quality images. So if we have this kind of tools, we can save time in content creation. And so I think it's also very interesting. So in the network, the advantage network is it can memorize some decisions human already made. So it can mimic the human's decisions. So that's the advantage of network. So if network learns how to do the decisions, I think it will be chance there. So the net give you an image. The network can automatically determine your input. So that can save a lot of time. Now we need many artists to work for that, right? So maybe we can produce tools, design tools to save the time for artists. Yeah, that's my basic answer. Yeah.
Automatic generation, right?
The automatic generation. So so graphics is something like a mix of art and the science. That's my understanding. Yeah.
That's the charm of it.
Yeah.
Just to follow up on that, then, do you think that deep learning does better in assisting the art or the science then?
I would give up the answer.
Yeah, so I think it's good if the deep neural network can do the artist work. So that's my point. Yeah, that's my understanding. Yeah.
It's especially kind of it's a laboring work, right? It's like a building.
Yeah, it's laboring work.
Yeah.
Okay, I think this is a nice point to conclude our discussion today. So I'd like to also thank our speaker and also Jiyong and also Weiwei for joining us today. We're very happy to have all of you guys as part of our seminar series.
Okay.
Yeah. Okay. Yeah. Okay. Yeah. So thank you for the wonderful talk and the comments. So for the audience, thank you all for the attention. Maybe let's finish the talk here.
Okay. Bye-bye.
Thank you.
Okay. Bye. Thank you.
Keep tuned next week for another talk.
Sorry.
Is there one more talk in the series, or this is the end of the? I think we have.
No. Oh yeah. We have one more 3D geometry and Weixin talk, but it's 3 weeks later. I think. Yeah.
Okay.
Right.
All right then.
Okay.
Bye-bye.
Thanks.
Bye-bye.
Bye-bye.